This is Lesson 4 in our Calculus 1 series, Calculating Limits. In the last lesson, we learned how to take limits graphically and numerically. In this lesson, we expand on the idea by introducing limit laws and talking about algebraic methods of finding limits. So let's take a look at these limit laws. If limit as x approaches a of f of x and limit as x approaches a of g of x exist, then we have the following limit laws. And remember that these limits existing is saying that the left limit is equal to the right limit, and that's a real number, not infinity or negative infinity. So if these two limits exist, then we get that the limit of the sum is the sum of the limits. So limit as x approaches a of f of x plus g of x is equal to the limit as x goes to a of f of x plus limit as x goes to a of g of x. So we could separate and take those limits separately when they both exist as real numbers. Same thing is true for subtraction. If we have a constant times our function inside the limit, we can pull that constant outside the limit. If we're taking the limit as x goes to a of the product f of x times g of x, and both of the limits exist individually, we can take the product of the limits. Same thing for a quotient. So let's take a look at this example. We can see from the graph that the limit as x goes to 1 of f of x is equal to 4, and the limit as x goes to 1 of g of x is equal to 2. So that means if we're looking for the limit as x goes to 1 of f of x plus g of x, we don't have the graph of y equals f of x plus g of x, but we can use this information to get the limit we're looking for. We can use the first limit law that says, because these limits exist individually, we can separate the limits and add them. And so this is the limit as x goes to 1 of f of x plus the limit as x goes to 1 of g of x, which is 4 plus 2, and that's equal to 6. Same thing for subtraction. Because the limits exist individually, we can separate and subtract, and we get a limit of 2 here. We're given the limit as x goes to 1 of f of x is equal to 4 by looking at the graph, but what if we want the limit as x goes to 1 of 5 times f of x? Well, we can pull that 5 on the outside of the limit, and so that's going to be 5 times 4, or 20. If we're looking for limit as x goes to 1 of f of x times g of x, and we know that the limits exist individually, we can just multiply those limits. And so here we get 8. And same thing for division. If we're looking for limit as x goes to 1 of f of x over g of x, and we know the limits exist individually, and that the denominator limit is not 0, then we can just divide those limits. And so here we get 2. So we can already see that these limit laws are expanding how we can use what we've learned in Lesson 3. Let's take a look at some more limit laws. Given that the limit as x goes to a of f of x exists, we have the limit as x goes to a of f of x to the nth power is equal to the limit as x goes to a of f of x, that limit taken to the nth power. So essentially what this is saying is that you can push this limit through the nth power operation. So in the example we had above, we know that the limit as x goes to 1 of f of x is equal to 4. If we want to define limit as x goes to 1 of f of x to the third power, we could push that limit inside the parentheses there. And so this is 4 to the third power, or 64. We also have that the limit as x goes to a of a constant c is that same constant c. In other words, as x is changing, this c is not changing. So this limit is just equal to c. We can think of that graphically as being the line y equals c. And as x approaches a, the y values are always the same. They're all c. We also have limit as x approaches a of x. Well, this is saying as x approaches a, what does x approach? Well, a. We could also think about this graphically on the line y equals x. As the x values approach a, the y values will also approach a. This limit law says limit as x goes to a of x to the nth power is equal to a to the nth power, where n is a positive integer, and this comes from laws 8 and 6 above. So here we know x is going to a, and then limit law 6 says we can push that limit inside the power function. We can do the same with root functions and with compositions with root functions. So if we have limit as x goes to a of the nth root of f of x, we can push that limit under the root and then take the limit. And I want to point out here two ideas that we're seeing with these limit laws 6 through 11. One idea is that we can pull or push the limit through some operations. So we saw that the limit as x goes to a of f of x to the nth power is equal to, we open the parentheses here, limit as x goes to a of f of x, all of that taken to the nth power. So we pushed this limit inside the power function. Same thing here with the root function. We push the limit inside the root function. And we're going to see many more operations or functions for which this is true in Lesson 5. Another idea that we saw here is that we can just plug in x equals a. Here we had limit as x goes to a of x is equal to a. Limit as x goes to a of the nth root of x is the nth root of a. This is called direct substitution to find the limit. And we're going to see more of this later in this lesson and also more in Lesson 5. So let's take a look at this example. We're given limit as x goes to 2 of f of x is equal to 1, limit as x goes to 2 of g of x is equal to 0, and limit as x goes to 2 of h of x is equal to 5. So let's find the limit as x goes to 2 of 3f of x plus h of x. So the first thing I'm going to do is make use of the first limit law that says this is going to be limit as x goes to 2 of 3f of x plus limit x goes to 2 of h of x. Now we make use of the limit law that says you can bring the constant outside. So this is going to be 3 limit x goes to 2 of f of x plus limit x goes to 2 of h of x. So that's going to be 3 times 1 plus 5, and that's 8. Here we have limit as x goes to 2 of 2 times the quantity g of x plus h of x squared. So first thing I want to do is take out this 2. This is 2 limit x goes to 2 of g of x plus h of x squared. Then we know we can push the limit inside this square. So it's going to be 2 bracket limit as x goes to 2 parentheses g of x plus h of x, all of that squared. And now we know we can separate these two limits because they both exist. So this is equal to 2 limit as x goes to 2 of g of x plus limit as x goes to 2 of h of x, all of that squared. And so this is 2 times 0 plus 5 quantity squared, so that's 2 times 25, and that's 50. Now let's take a look at the direct substitution property. If f of x is a polynomial, a rational function, or a trig function with x equals a in its domain, then limit as x goes to a of f of x is equal to f of a. So if you're taking the limit of a polynomial, a rational, or a trig function, and x equals a is in the domain of that function, you can just plug in x equals a. So for example, limit as x goes to pi over 2 of sine of x. We know that pi over 2 is in the domain of this function, so this is just sine of pi over 2, which is 1. Here, limit as x goes to 3 of 2x squared minus x plus 1. We know that polynomials have a domain of all reals, so certainly we can just plug in the 3 here. And so we have 18 minus 3 plus 1, so we have 16. Here we have a rational function. As x goes to 1, we're looking at the limit of 3x minus 1 over x squared plus 1. X equals 1 is in the domain of this function, And so we can just go ahead and plug in x equals 1, and we get 2 over 2, or 1. And so we note here that the direct substitution property requires x equals a to be in the domain of the function. But let's take a look at a situation where we can get around that. What about something like f of x equals x squared minus x minus 2 over x minus 2? This expression can actually factor and simplify to x plus 1. But notice x equals 2 cannot be in the domain of the original function. So this function is the same as the line y equals x plus 1 at every x value except x equals 2. At x equals 2, f of x does not exist. It's not defined. So that says that its graph is going to be the same as the graph of the line y equals x plus 1, but it's going to have a hole in the graph at the point where x is equal to 2. So what happens if we want to take the limit as x goes to 2 of x squared minus x minus 2 over x minus 2? We can't plug in x equals 2. This is a rational function, but x equals 2 is not in the domain, so we can't plug in x equals 2. But we can see from the graph that this limit exists and is equal to 3. So let's see how we can compute that algebraically. We can factor our numerator, and we can cancel the x minus 2. Now we know that this original function and this simplified function of x plus 1 are the same at all x values except x equals 2. Well, that's perfect for limits because limits are not concerned with what's happening at x equals 2. They're only concerned with the behavior as x approaches 2. And as x approaches 2, x is not equal to 2. So these limits are the same. And now here we can just plug in direct substitution. So if we're taking the limit of a rational function, and we know that this number is not in the domain of the rational function, we first want to see if we can factor and cancel. And then, if we can just plug in. So again, here I'm just specifying that the original function does not exist for x equals 2. The simplified function does, so the functions are the same for all x not equal to 2. And since limits aren't concerned with what's happening at x equal a, they're concerned with what's happening as x approaches a, the limits are going to be the same. And so we have a more generalized statement here that says if f of x is equal to g of x for x not equal to a, then the limit as x approaches a of f of x is equal to the limit as x approaches a of g of x, provided the limit exists. So let's take a look at this example. We have limit as x goes to negative 1 of 2x squared plus 3x plus 1 over x squared minus 2x minus 3. We try plugging in x equals negative 1 using direct substitution, and when we do that we get 0 over 0. So for a rational function, that should tell us we should be able to factor an x minus a negative 1. In other words, an x plus 1 should factor here and cancel. So we factor our numerator and we factor our denominator, and sure enough we see the x plus 1 in both cases, and so we can simplify and we know that these limits are equal. And at this point we can just plug in x equals negative 1. So here we get 1/4. Let's take a look at this limit. Limit as h approaches 0, 4 plus h quantity squared minus 16 over h. So we try plugging in h is equal to 0, and we get 0 over 0. So we're hoping that we can cancel a factor of h in the numerator and the denominator, similar to what we've been doing before. In order to do that, we're going to have to expand and simplify the numerator. So we expand the 4 plus h quantity squared. That's 16 plus 8h plus h squared. And so now we see that our 16 and our negative 16 are going to cancel additively. And then we can factor out an h from the numerator. We can cancel the h's. And at that point, we can now plug in h is equal to 0. So up until the point where we cancel, we can't plug in h is equal to 0 because we'll still get 0 over 0. But once we do that canceling from the numerator and denominator, then we can plug in the h equals 0, and then we get our solution. And so this limit is equal to 8. Let's take a look at another. This one looks a bit more complicated because we have a radical. Limit as u goes to 2, radical 4u plus 1 minus 3 over u minus 2. Now, if plugging in 2 did not give us a 0 in the denominator, we'd be able to use our limit laws and just plug in. So again, we want to do some math on this and hopefully factor and cancel a u minus 2 from the numerator and denominator. And then we'll be able to plug in u equals 2. So that's the goal, and let's see how we can get there. In order to simplify the numerator into something that contains a u minus 2 factor, we're going to have to get this u out of the radical. So we want to rationalize the numerator here. So we multiply our fraction by the conjugate of the numerator over itself. So notice here we had a subtraction between the terms. Now we're going to multiply this by its conjugate, meaning having an addition between the terms. We switch the sign and take that over itself. So we're multiplying by a fraction that's equal to 1, so we're not changing the quantity, we're just changing how it's written. And then multiplying through the numerator, we need to FOIL that out and expand. We get radical 4u plus 1 quantity squared minus a 3 radical 4u plus 1 plus a 3 radical 4u plus 1, and then minus 9. So our middle terms are going to cancel here. Our radical and our square cancel each other, so we have 4u plus 1 minus 9 over u minus 2 multiplied by radical 4u plus 1 plus 3. And generally speaking, it doesn't pay to expand the denominators. It's usually the numerators that need to be expanded and simplified. So I'm just going to leave this factored in the denominator. Simplifying the numerator, we get 4u minus 8. So we can factor out a 4 and see that we have a u minus 2 factor in the numerator. That's great. That's what we were hoping for because that will cancel here. And now we can plug in u is equal to 2. And simplifying gives us 2/3 for this limit. Let's take a look at another. Here we have limit as h goes to 0, 1 over x plus h quantity squared minus 1 over x squared all over h. Again, if we try plugging in h equals 0, we're just going to get 0 over 0. So we hope to do some algebraic manipulation on this so that we can cancel a factor of h in the numerator and denominator and then plug in h equals 0. So what can we do here in the numerator? Well, let's combine fractions. So we'll multiply the first fraction by x squared over x squared, multiply the second by x plus h squared over x plus h squared. This way we'll have a common denominator. And so our numerator now looks like this. And just to get rid of the double-decker fraction, dividing by h over 1 is the same as multiplying by 1 over h, so that h goes into the denominator here. And let's expand and simplify in the numerator. Remember when you're FOILing out here the x plus h squared, if you have a negative sign in front of that, that negative sign needs to apply to all of the terms that you get when you expand. So make sure to use parentheses there. And now distributing that negative through the parentheses, we're here. And we see that we have a positive x squared and a negative x squared. And what remains in the numerator, all the terms have a factor of h. So we can factor out that h and cancel with the h in the denominator. Now at this point, we can plug in h is equal to 0. And so our limit here is negative 2 over x to the 4th. Now another technique that is useful with evaluating limits algebraically is using left and right limits. So for limits involving piecewise functions, we often need to check left and right limits separately. So for example, here we have f of x is defined to be 2 minus x squared for x less or equal to negative 1, x plus 4 for x between negative 1 and 2, and x squared plus 2 for x greater than or equal to 2. So we've got this piecewise function here. And we're asked to find the limit as x goes to negative 1 of f of x and the limit as x goes to 2 of f of x if they exist. So we're talking about the two values, negative 1 and 2, at which the function definitions change. We're interested in the limits at those points. Do those limits exist? Well, for limit as x goes to negative 1, we need to consider the left limit and the right limit because the function definitions are different for x values to the left of negative 1 and for x values to the right of negative 1. For x values to the left of negative 1, we're using this top function 2 minus x squared. So for the limit as x goes to negative 1 from the left of f of x, this is the limit as x goes to negative 1 from the left of 2 minus x squared. And this we can just plug in. It's a polynomial function. So this limit is equal to 1. But the limit as x goes to negative 1 from the right is going to have to use this function, x plus 4, because x being greater than negative 1 falls into this category. So the limit as x goes to negative 1 from the right of f of x is the limit as x goes to negative 1 from the right of x plus 4. Again, polynomial, we can just plug in the negative 1, we get 3. And we notice that the limit from the left is not equal to the limit from the right. So that says the limit as x goes to negative 1 of f of x does not exist. Now let's see what's happening at x goes to 2. I want you to take a few minutes, pause the video, and work on this problem on your own. Consider the limit from the left and the limit from the right the same way we just did for x going to negative 1. So please pause the video and work on that. So the limit as x goes to 2 from the left of f of x is going to be using the function x plus 4 because the x values to the left of 2 fall into this set. And so this limit is equal to the limit as x goes to 2 from the left of x plus 4. We can just plug in here, and so that gives us 2 plus 4, which is equal to 6. And the limit as x goes to 2 from the right of f of x needs to use this function, x squared plus 2, because the x values that are greater than 2 fall into this set. So this limit is equal to limit as x goes to 2 from the right of x squared plus 2. 2 squared plus 2 is equal to 6. So these left and right limits are the same, and so our limit as x goes to 2 of f of x exists and is equal to 6. So again, with piecewise functions, you're going to want to find limits by taking left and right limits separately. And so for limit expressions involving absolute value, we need to express the absolute value in its piecewise notation and then check left and right limits separately. So don't forget that absolute value is really a piecewise function. And so when we see something like this, limit as x goes to 5 of absolute x minus 5 over 3x minus 15, we want to remember that this absolute value function is really defined piecewise. And we want to use that and check left and right limits separately. And we want to do this when we notice that x is going to the number that makes the absolute value expression 0, because that is where the definition for the function changes in the piecewise notation. That's why we need to use the left and right limits here. So I've written the absolute x minus 5 here in its piecewise notation. We know that the absolute value of something is exactly that if that is a positive number. So absolute x minus 5 is equal to x minus 5 for x minus 5 greater than or equal to 0. In other words, for x greater than or equal to 5. And we know that absolute x minus 5 is equal to negative of x minus 5 when x minus 5 is less than 0. And so that's saying when x is less than 5. So now taking this limit from the left, we're talking about x values that are less than 5. So we're going to use this bottom function here. So we replace absolute x minus 5 by its function definition here, negative of x minus 5. We can simplify here by canceling factors of x minus 5. And so this is equal to the limit as x goes to 5 from the left of negative 1/3, which is just negative 1/3. And that's our limit from the left. Let's take a look at our limit from the right. Our limit from the right has absolute x minus 5 being replaced by x minus 5. Because as x goes to 5 from the right, those x values are bigger than 5. And that falls into the top category for this piecewise function. So we're here. Again, we factor and cancel an x minus 5. And so now we're taking the limit of 1/3, which is just 1/3. And so we notice that our left and right limits are not equal. And so this limit, the two-sided limit we were asked to find, does not exist. And with this, we'll conclude our lesson on calculating limits.